So we have the last talk in the morning session. Pascal Barla is from France and is going to talk about the material quality in the eye of the beholder.
Okay. So first, thanks for inviting me to this conference. I'm glad to be here. And my presentation is going to be about material qualities, which is one of the central topics, I guess, of Shitsukan research. And I'm going to talk about it from a computer graphics perspective. So there are two aspects of material, at least, that are interesting. There are mechanical and optical properties. So for instance, if you look at this photograph, the fact that the ground will be hard or soft to the touch, or slippery or stable, is determined by mechanical qualities, the properties. Whereas the optical properties will characterize how the light gets reflected when you walk on the path. And both aspects are very interesting, but are mostly focused on optical properties in this talk. So the question I'm interested in is how is light affected by matter? But first, I'd like to consider whether we can give an objective answer to that question. So usually in graphics and optics, material is it's thought like a summary of light transport on a microscopic scale. So for instance, it's a summary of how light is scattered at a point like this here. And so the more light is scattered, the more you will have blurry reflections. And a way to formalize that is through the BSDF, which stands for bidirectional scattering distribution function. So it is bidirectional because it takes two directions as input, the incoming light and outgoing view in orange and blue arrows. And it outputs reflectance or transmittance distribution. Here I show the reflectance distribution in blue. But what's kind of odd with this definition is that it seems that scattering takes place at a single point. Well, actually, if you come back to the original definition by Nicodemus and colleagues, you'll see they consider a more general setting at first. A large irrigated area where the light that comes in can exit at the different points. So it means that locally you can have subsurface scattering. But they go on to say that at the right scale, you can squeeze that region to a single point, and this is how you obtain the BSDF. So it means that implicitly, when you take a BSDF, it makes an implicit choice of scale, which is not very objective. But maybe there's an objective way to characterize scale, a single scale. So let's look at this object, and in particular, let's zoom on part of the material, which is ceramic. And as you zoom in, you'll see more and more shapes, which are made of materials, which themselves are made of shapes, which are made of materials, etc. So I think there is no a priori objective way to choose a single scale. However, you might say, okay, but in everyday life, shape is what's visible to the naked eye, so material can be considered as what's invisible to the naked eye. And in this context, in graphics at least, microfacet theory has been very successful. It posits that the microsurface on microscopic scale is made of a myriad of tiny mirror-like microfacets. And the more disordered these microfacets, the rougher the material will look like, as you can see here. But you never actually see a single microfacet. What you instead control is this. So this is a statistical microfacet distribution that characterized in the top-down way the material itself. So what it tells you here at the center is the proportion of microfacets that are aligned with the surface normal. And if you go to the sides, it gives you the proportion of microfacets that are tilted away from the main surface. So the width of this distribution tells you how rough a material will be. And this is a very useful mathematical construct because it permits to give analytical formula for direct single scattering, so when the light hits a single microfacet. And there are also recent models that deal with interreflections among microfacets. But in any case, you have to pick and choose a distribution, which is a bit subjective. And usually people prefer this kind of distribution, the Trowbridge-Wright, which is also called GGX, to earlier distributions like Beckman, because they have stronger tails distribution. Actually, there are other models, like for instance, the model of Lowe, that have even stronger tails that are even closer to physical references, but they are less convenient to manipulate for mathematical reasons, but also for artistic reasons. So there's a compromise here as well, which is subjective. Anyways, microscale roughness is just one ingredient of what's today called physically based rendering, or PBR for short. You have other ingredients like translucency or special models for clouds, for instance. And usually artists, they combine these different ingredients without ever having to think about how the material look on microscale. A very good example of that is given by the website Shader XYZ. So they organize contests where they show a photograph like this one and ask artists to reproduce the appearance of the photograph starting from a 3D scene. So here are the results of two different artists. They actually use the same renderer, V-Ray, and obtain pretty faithful results. But if you look at their shading graphs, which show how they combine different ingredients, the little box are different ingredients, you'll see they take very different approaches. So again, this is a very subjective process. And last and not the least of the subjective aspects of material modeling are texture maps. This is very important in visual effects and video games, where these industries have come up with workflows, which is a set of textures that can be exchanged between software. And among them, you have, for instance, the base color that controls the color of diffuse materials or metallic materials. You have the roughness that controls the aspect of specular reflections. But you also have, interestingly, geometry-related maps, like height and normals that control coarse and fine relief, and ambient occlusion that control occlusion in cavities. And what's really impressive is that with these textures, you can achieve really realistic renderings, even though the underlying material model is limited. So in a way, they mask the limitations of the underlying model. So what I wanted to point out in this rather long introduction is that I think that material modeling is a subjective business. So to recap, you have to choose a scale. Then you have to decide whether you use a statistical description or not. If you do, you have to choose a distribution model. And usually, you'll have to combine multiple ingredients or components and make them spatially varied. So at this point, you might wonder, but what makes a new material model interesting? What makes it a new contribution? And I personally think that it's partly subjective and objective. On one side, there are all the effects you see in your surroundings and you want to reproduce, and that's the subjective part. And on the other side, you have to make sure that existing models either are not able to reproduce these effects, or they are too slow, or they are too hard to control. And if any of these conditions apply, then there is a contribution to be made. So I'm going to present you 3 projects in the following along these lines that work at 3 different scales. So the first one is going to be on iridescent and works on a nanoscopic scale. The second one on layered materials, microscopic scale. And the third one is going to quickly present the importance of mesoscopic surface details for the case of wet surfaces. Okay, I'm going to start with iridescence. So this is a work that was published 2 years ago at the SIGGRAPH conference and done in collaboration with Laurent Becourt. So we obviously got interested in iridescent colors because they are very vivid and attractive, like in soap bubbles or leaf beetles. But the more we worked on that topic, the more we realized that iridescence is everywhere around us in more subtle configurations. For instance, if you have a dish and you have a thin layer of grease, you can observe iridescent colors, subtles, but they're here. And you also have them in oxidized metals, for instance, and many other examples. And one way to reproduce this iridescence is through thin films. So let's start with a metallic object, like the one on the right. And on the microscopic scale, it's smooth, like depicted on the left. And if you add on top of that a thin film of a thickness that is very low, it's on the orders of hundreds of nanometers, then what you obtain on the right is, well, iridescent colors. And that's surprising at first. Like, why would you have iridescent colors with just a simple film on top of it? Well, to understand that, you need to look into the wave nature of light. So here, the arrows actually carry waves along them. And to understand thin film colors, you need to understand interference. So the wave that reflects off the top interface, the blue one, is going to interfere with the wave that reflects off the bottom interface, the green one. So to understand that, let's look at the waves in this representation. In this case, the 2 waves are out of phase. So when I add them together, the amplitude is smaller. And this is what we call destructive interference. But you could have also the 2 waves to be in phase. You would have constructive interference. And what's really important to distinguish the 2 cases is the phase offset, which is usually called the optical path difference, D. And D depends on many different things. Of course, it depends on the thickness of the layer, but it also depends on the direction, on the angle that the incident light takes, and most importantly, on the wavelength. And why is it's important? Because for different elevation or angles and for different wavelengths, you'll have destructive or constructive interference. This will create complex spectra, which in the end lead to iridescent colors. So actually, these are not the only paths that light can take in the material. You can have multiple bounces inside, but then you have multiples of the optical path difference. So that's the same story. And this was formalized a long time ago by IRI, now can call it in the rest of the presentation IRI reflectance. And well, we could use that right away, but maybe you can see already the problem with IRI reflectance is that it's based on wavelength, lambda. And usually in graphics, we use RGB renderers. Well, a Naïve solution to that is to, well, pick 3 wavelengths, one for each color channel, RGB, and render using this equation. And you obtain this result, which looks fine until you compare it to reference. And then you see now the colors are off. And actually, the reference is rendered with 128 samples in the spectral domain. So what it means is that you really need to have a lot of samples in wavelength in order to capture the subtleties of thin film reflectance. But this takes too much time, so we thought we need to look for a better approach. So to explain it, I'm going to take a very simple scene where you have one light source, one object, and a sensor. And each of these components have their own spectral properties. So the light source has an emission spectrum, the object spectral reflectance, and the sensor has XYZ color matching curves. And so what we're interested in when we're rendering is to have a XYZ color that you can then convert to RGB. And to obtain this, you need to, well, integrate the product of the 3 terms over all wavelength. Well, we're going to make a first approximation. We're going to assume that illuminant is smoothly varying per color channel, so it can be taken out of the integral. But you're still left with this complex integral of the product. So let's look at the reflectance now. Well, when we look at it, it seems that it has these nice oscillations. And actually, if you make a simple change of variable and look instead at the inverse of wavelengths, then you have really nice oscillations with a more regular period. And actually, in the paper, we found that area reflectance can be re-expressed as an infinite series of cosines, a sum of cosines. And what's really nice about that is that when you turn cosines and transform this in Fourier space, then you obtain Diracs. And not only do we know analytically the magnitude of each Diracs, but the spacing between Diracs is directly related to the optical path difference that I talked about before. So that's a very, how to say, compressed and elegant way of talking about the thin film reflectance, but how can we use it? Well, remember that we had to compute this complex integral that I'm going to squeeze here just for space. And so that's a continuous integral in the spectral domain. Well, the nice thing is that now if we take the XYZ matching functions and convert them to Fourier space and do the same for thin film reflectance, well, what we turn this is we turn it into a discrete sum in the Fourier domain. And this equality is actually guaranteed by Parseval's theorem. Again, the paper explains that in details. But that's the main contribution of our approach, turning a continuous integral into a discrete sum that's much, much easier and faster to evaluate. So you don't have to do all these spectral samples. But maybe you realize that until now I was only talking about materials that are smooth on a micro scale. So what about rough materials? Well, there's a way actually to integrate that easily in microfacet theory is to assume that each microfacet is actually coated with a thin film. And so usually microfacet equations look like that. It's a product of 3 terms, so the distribution that I talked about in the beginning of the talk. Then you have the term G, which accounts for masking and shadowing by microfacets. And finally, you have the reflectance, which is usually modeled with Fresnel equations, which is F here. Well, in our approach, we simply replace F by R, the airy reflectance, and we use our integral. And that's it. There's nothing much more to do to obtain results. So I'm going to show results. So the method works in real time and offline, but I'm going to show only offline results because they are more pretty. OK, so first on the left, we start with a leather chair to which we're going to add a thin film of uniform thickness. And you can see it adds subtle but noticeable color overtones, bluish and purplish colors. The method also works on top of metallic bases. Here we start by increasing the thickness of a homogeneous film, and then we're going to vary it specially to have patterns that change in color when you change the point of view. And finally, the method also works straight away with transparency, which at last permits us to obtain nice soap bubbles. So the method has some limitations. Another approximation we make to make it work is to assume that the index of refraction of the base material is also smoothly varying per color channel. So it works for most materials like glass or mercury, but some materials like copper create approximations that are not as good, as you can see in the comparison. And before moving to the second project, I'd like to give some insights that I had rather recently. I was looking at films, thin films that increase in thickness, like a soap film on the left that increases in thickness due to gravity toward the bottom, or oil slick that increase in thickness toward the center. And what you can observe is that when it increases in thickness, you obtain these kind of alternations of bluish, greenish colors and pink colors here and there. And I was wondering why. Why is that so? Well, if we start again from the color matching functions, and now turn them in Fourier space, like we do in our approach, what I show here is the real part of the x and y matching functions. Our approach tells us this. So first you have to pick a Dirac at the center at 0, and it gives you a gray color. And then you at least need to take into account another Dirac. And and that's at the distance, that is the optical path difference. Now if you increase thickness, you will increase the optical path difference. So you will move along this line, like this. And as you can see, the colors that you can see at the bottom here are directly related to the two color matching functions, which are out of phase at the end of the spectrum. And this means that this repetition of colors is directly due to our photoreceptors. Or in other words, with a different animal, with different photoreceptors, you will not only have different colors, but also different oscillations, different fringes, and different repetitions, which is interesting. Okay, now I'm going to move to the second project I want to present today. So it's an ongoing work with Megan Batty and Roman Bakanovsky. And it's about layered materials. So layered materials are all around us, not only in man-made objects like Christmas balls and car paints, but also in nature, in leaves, petals, skins, etc. And they have something special about them, is that the reflections look somehow more sophisticated and the color deeper. And we were wondering whether we could characterize these visual qualities. So first, what do we mean by a layered material? Well, it's a stack of interfaces, so multiple interfaces. It can be rough, and they are described in our approach statistically, like with a microfacet approach. And in between these interfaces, you have absorption or scattering, so you can absorb colors or scatter light. And what we're interested in is to connect the physical properties of this layer stack to the visual qualities of the layered material models. And in the long term, maybe try to inverse that from visual qualities to physical properties. So the problem with this, with layered materials, is that even rendering them is challenging. So there are different approaches. The first approach is to use simulation. So classic Monte Carlo simulation, except that you don't deal with a general 3D scene, but with a simpler layer stack. So you can make some approximations. For instance, delta X here, which shows the lateral displacement of rays, can be ignored in practice in a material. And it gives interesting results. It's faster than classic Monte Carlo rendering, but still you need to make it converge, and you can observe a little bit of noise sometimes in your results. An alternative approach is the layer lab approach, which was developed by Jacob and colleagues, Wenzel, which is here today, who is here today. And the idea is to, in a pre-process, project the reflectance and transmittance of layers and interfaces in media on a Fourier-based representation. And the advantage of that is that you have noise-free results in the end. An inconvenient drawback is that when the interfaces start to be really smooth, then you have ringing artifacts, and the preprocess takes more time and more memory. But in general, the main limitations of these two approaches in our objectives, our objectives, is that these are black boxes. So that won't really help us connect physical properties to visual qualities. So we turn our interest to attention to layered material models. So a first kind of model is a recursive is based on a recursive approach and was pioneered by Waldish and Wilkie. So the idea is you take the two directions of the BSDF, so the incoming and outgoing directions. In the first step, you evaluate the reflectance of the first interface. Then you refract the two rays in the second step. And in the third step, you assume they meet at the same point, which is an approximation. And you evaluate the interface there again. And you do that iteratively until in the fourth step, when you come back up, you account for transmission through interfaces. And this gives really nice results, but it's not clear how the approximations or the models impact the results. For instance, there is no interreflection inside a layer in this case. A more recent approach is based on forward propagation. So a bundle of light rays is propagated through the layer stack. And the statistics of this bundle are updated. So the statistics are the energy, the mean direction, and the variance. And they are updated at each event: reflection, transmission, and even scattering. And in the end, you have multiple lobes for each layer, as you can see here in colors. And again, the results look very nice, but it's not clear, again, what is the impact of the use of statistics as an approximation on the results. So to figure that out, we conducted a numerical analysis. So we consider layered materials made of only two interfaces. With the medium in between, they can be absorbing but not scattering, because there is not yet any good model for dealing with scattering in layered materials. In total, we obtained 60 different test materials that are constructed like this. So we have on top a coating that can be rough and colored that we add either to base Lambertian or diffuse material, which gives plastics, on the base conductor material, which gives metals, and on the base dielectric material with the air at the bottom, which gives transparent slabs. And so we did an extensive analysis of these materials. That's in a research report. But here I'm just going to show quickly our results. We also improved a little bit the previous models, and I'm going to use these improved models. So let's look at plastics first, like rough coating on the plastic. So here on the left, you see the reference simulation, and on the right, you see the results of the recursive model, which is noticeably darker. I think we can see that a little bit on the screen. And the reason is that it doesn't take into account the reflections. I don't show the forward model in this case because it simply doesn't work with the Lambertian basis. Now, if we turn our interest to metals, for instance, metallic paints, we have a smooth interface on top. This time, the recursive model gives nearly perfect results. And the forward model is pretty good as well, slightly brighter, even if it's hard to see here. Where the forward model really shines, though, is when you switch the roughness of the interfaces like this. And so you have material that is like a frosted metal, for instance. Now, the recursive model doesn't work very well, but the forward model gives a really good approximation. So to recap quickly, the only model that deals with all configurations is a forward model, but it doesn't work on the Lambertian base. And I've not talked about it here, but also it works with transmission with pretty good approximation. And again, scattering is not really well handled in existing models. So it means that in the future, we'll have to probably work on combining these two approaches. But still, this analysis, during this analysis, we found interesting visual qualities of layered materials. I'm going to show here quickly. First, concerning diffuse materials, we found that it was possible to have materials that have a fixed normal albedo here in the center of this sphere, but varying grazing albedo by changing the parameters in a smart way. And so this is what I'm showing here. I think you can see it on the projector. You can have the choose a color tint toward the grazing angles in this case. The same idea can be achieved with a layer of smooth interfaces. Here I'm using 3 different interfaces with 3 different index of refraction. You can have a fixed normal reflectance at the center and a different varying grazing reflectance at the borders, like this. And this is only possible with layered materials, actually. And the same idea can, again, be applied this time to roughness. So having the same roughness at the center, but a different roughness at grazing angles, like that. Or the opposite. Same roughness at the grazing angles and different roughness at the center, like that. So what these empirical observations show is that it's probably possible to find and maybe even control visual qualities of their materials. And what we want is to tie them to physical properties in ongoing work. So okay, now I'm moving to the last project I'm going to present today on wet surfaces. which was more like an experiment that we did in the context of an internship with Loïc Lachiver and Gaël Gainbo. So we got interested in wet surfaces because they show interesting spatial variations, which are not only due to the base material, but also to mesoscale details of the surfaces. But first, what happens when you add water to a dry surface? You have mainly two different optical effects. The first one, which is numbered 4, is that you have new specular reflections due to the water layer. But you have a second effect, which is to have darker and more saturated colors, because the light paths are lengthened inside, they are longer inside the material. And because they're longer, they get more chances to be absorbed inside the material. So they are more colored and darker. And this is even more true for porous materials. So actually, we looked around, and there is this substance designer software where they have a specific water level node where they basically mimic these effects, where you can add a layer of water, and it actually changes the textures that are used for rendering. It's only changing the texture, not affecting the shading, the different textures I showed at the beginning. But we thought it's interesting they don't deal with something that's important in water, which is surface tension. And so we identified 3 different surface tension effects that we wanted to reproduce. The first one works at the mesoscale, and it's called the meniscus. It's this shape that the water takes when it meets a new material. It takes a different angle, a specific angle, depending on the material. Another effect is, that works at the mesoscale are the puddles that are shown here. So the layer of water is coating the convexities, but in concavities it can create small puddles. And visually, as we're going to show, it has an importance. And the last effect works this time on the microscale. When you have a porous material and you put water on top of it, when the water starts to get inside, it takes on the shape of the microsurface of the porous material. And this creates a transition in roughness. So in our approach, the first thing we did was to identify different zones of a wet surface. So we identified essentially 3 zones. So the immersed zone, where the water is on top of the base surface, the wet zone, where the water is coating the base surface, and the moist zone, where the water has penetrated inside. And of course, you also have the dry zone outside of that. And so regarding surface tension effects, the meniscus occur at the transition between immersed and wet zones, the puddles in the wet zones, and the roughness transition between the wet and moist zones. So the first thing we had to do was to identify these zones. So we started from 8 map, and from this we extracted a zones map with the same color code I'm using here. And now we use this zone map to control other filters on other textures, as I'm going to show. So start with the base color map. That's the simplest one. The thing we do is that we simply make it darker and more saturated, following previous work, in all zones except the dry one. Now the roughness map is a bit more interesting. In the immersed and wet zone, we're going to make the roughness equal to 0, means the surface is smooth. But we'll also take care of the roughness transition here by having a transition from wet to moist regions. This is a microscale effect, but all the mesoscale effects occur in a normal map. So first thing that happens is that some parts get flattened because they're part of the immersed region. And some other parts, you won't see that in detail, I'm going to show that in a video afterwards, are the puddles and the meniscus that occur also here. And we optionally change the ambient occlusion map, brightening it in the immersed region to account for refraction. So now, let's go back to the first version of the water level node, the one which is shipped with a substance designer software. As you can see, the bricks doesn't look that wet in these results, and also the immersed zone look more like a mirror surface, and there is no moist region in sight. In comparison, our first results, empirical results, looks like this. The bricks look more wet thanks to the puddle effects, and also the surface, the wet surface, the immersed surface doesn't look like a mirror anymore, thanks to the meniscus. And you also have this roughness transition in the background that depict porous material. Okay, and just before concluding, I'd like to show some interesting failed attempts we had. at the beginning we started to just try, well, why not try to smooth normal maps? And we did it in different ways, and what was interesting is that it made the materials look made of a different viscosity. So the left one more glazed to me, and the other one more sticky. It's just my impression. So I think there is interesting future work to be done here to try to understand why this is the case. So okay, I've presented you with 3 different projects that work at 3 identified scales, but in practice, in particular in nature, things are not that simple. For instance, the leaf beetle I've shown at the beginning is not actually implemented in nature with a thin film. It's more complex than that. It's a multi-film, so it's layered material on a nanoscale. And some of them have even helicoidal structures that affect the polarization of light, so it's really difficult. You might also have a mix of scales. For instance, this tulip has a diffraction, which is nanoscale as a first layer, and then a classic multi-layered material. And this achieves this very complex reflectance. And you might even have effects on the mesoscale. So pearl, for instance, they have like a multi-film on a nanoscale with lateral scattering in each of the layers. Plus, because it's curving, the scattering is very specific, and that's affected by the curvature of the pearls. So that's a mesoscale effect. But I think we should also take inspiration from art and vision. For instance, I really like this painting by John Singer Sargent because you can really see the gloss in the statues, and even I have the impression that the statues are wet. Maybe I know this is a fountain, but I really have this impression, and I thought maybe this is all in my mind. And actually, it's really all in my mind because the brushstrokes are really obvious when you look at them carefully. And this is something that was called the Beholder's Share by Ernst Gombrich in his book Art and Illusion. The fact that the artists rely on our expectations and that we fill the gaps in a way of the painting. And what I hope I'll have convinced you is that this is obvious in paintings, but it also occurs in physically based rendering, and maybe even in real life. So I'd like to thank my collaborators again, and thank you for your attention.
Thank you. Yes, David.
You started with the observation that materials have mechanical and optical properties. And of course, one of the reasons that visual perception of materials is useful is it allows us to make inferences about the mechanical properties of objects. I'm wondering whether the sort of physical models that you're building for the optical properties might also allow prediction of mechanical properties and thus tell us more about the fundamental reason these things are correlated.
So usually when we talk about optical properties, we look at rather small scales, like microscales. And my own idea on the topic is that it depends, because in actual software, people, what they call the material is also the mesoscale structure, like substance designer is also designing textures. In this case, then the way you manipulate the mesoscale, I've shown that a little bit with wet surfaces, can really affect, I think, the filling of mechanical properties. So I think this is going to happen mostly at the mesoscale level. But I might be wrong. I say mostly, not all the time. So there is probably much more to be done in this respect. What's interesting here is that it's completely static. And that's what I find interesting. And also you have dynamic behaviors. When you have dynamic behaviors, the microscopic aspects might be important because you might have a change of shininess and things like this. But in static cases, I think the mesoscale properties are the most important. But that's just a feeling right now. It deserves more research.
Any more questions?
Thank you very much. And yeah, in relation to the earlier talks, probably the people are interested in using your technique like wetness, very realistic wetness thing as changing the appearance of a food or something. But probably in that case, it's very difficult to measure actually physically what happened in each case. In this situation, you assume some models, but in the real situation, in particular for the real food, it's hard to model it. So is there any good suggestion on how to make a good workflow to apply this kind of very physical based technique to the real situation?
So yeah, I have to insist that the case of wet surfaces is really taken from a graphics perspective, where you manipulate normal maps and things like this. It's only distantly related to what you would have with a measurement. So also this is what I find interesting, because you can manipulate things more in this case. Now, if you would like to measure it, I think it's quite difficult, because you would need in some way to measure the two different layers, like the underlying layers and then the moist layer on top of it. You could do that in 2 steps, but in some case, adding a liquid on top of an initial surface, especially if it's porous, it affects it as well. So I'm not a specialist of material acquisition, but that's probably an interesting challenge there. You cannot really do this in 2 steps, I think, unless the base material is really not porous at all. In this case, it won't be affected by adding liquid on top of it.
Thank you.
Any more questions? No? Okay, so thank you very much. Thank you.